talk today, I'll give you a few minutes of just some introductory material on gamma ray bursts just to get everybody on the same page. Spend a few minutes talking about the progenitors of the long duration GRBs and why we know that they're massive stars, and then use that to contrast with the observations of the short GRBs. And show you several lines of evidence that from observations we've been carrying out over the past few years, suggesting that the progenitors are indeed these compact object mergers. And then I'll talk about how we can use this information for follow-up of advanced LIGO gravitational wave sources. And I'll show you some results from our follow-up observations of the first events detected by LIGO. By the way, if there are questions, please feel free to jump in with questions. I'm going to try to cover quite a lot of material. So gamma ray burst, the whole field started with the accidental discovery of these bursts of gamma ray radiation coming from outside of the solar system. This is the first one that was detected back in 1967. The field for the first 25, 30 years more or less proceeded with very little observational information and a lot of theoretical ideas. But in the early 1990s, the BATSI experiment on the Compton Gamma Ray Observatory led to the localization of a large number of gamma ray bursts that showed a uniform distribution on the sky that was suggestive of an extragalactic origin. And that was finally confirmed directly with the discovery of afterglows, so counterparts at longer wavelengths, X-rays, visible light, radio waves, which provided precise positions and identification of host galaxies that showed that these events are indeed cosmological. And in fact, the most distant gamma ray bursts that we know of today are extend to redshifts 8 and 9. So they're quite distant. The other key result that came out of this large sample from BATSI is that there are actually two kinds of gamma ray bursts. So if we plot the distribution of durations, you can see that there are two peaks, one shorter than about a second, which we call the short burst, and the other one at tens to hundreds of seconds, which we call the long burst. In many respects, they look identical except for their duration. So the sample that we're working on these days from the SWIFT satellite is primarily long duration GRBs. 1 out of 10 is a short burst, which means that the rate of discovery is about one event per month for the short GRBs. So it takes a while to build up a sample that's big enough to give us the properties of these sources, and so we've systematically been studying them and trying to build up samples of tens of events. We have a general framework in which we understand both the gamma ray radiation and the afterglows from gamma ray bursts. And that model has essentially three ingredients. There is some sort of progenitor system that is hypothesized through various processes to give rise to a black hole that's rapidly accreting. And the most popular ways of making that is through the core collapse of a massive star or by merging two neutron stars. That accreting black hole then launches a relativistic outflow, which contains instabilities and leads to the very bright gamma ray radiation. So it's collisions within this unstable outflow that lead to this spiky structure in the gamma ray emission, lasting, as I said, anywhere between a fraction of a second to hundreds of seconds. And then eventually this outflow interacts with the medium surrounding the progenitor system and produces what we call the afterglow radiation. And the afterglow radiation propagates from initially X-ray, primarily X-rays, to then visible light and eventually radio waves. Okay, so you can see here an example of an afterglow, the X-ray emission fading away, the optical emission fading away, the radio emission getting brighter and then subsequently fading away. You can see that unlike the gamma ray burst, which only lasts for about 100 seconds in this case, here the afterglow emission is detected for many days and even weeks and months in the radio. So the real characteristic of gamma ray bursts, the thing that separates them from normal supernova explosions or other types of transients, is not the energy scale. Actually, the energy scale in a gamma ray burst is very similar to a normal supernova. It's the fact that the outflow is highly relativistic. The Lorentz factor initially is hundreds, and even during the afterglow phase, it's tens, and that the outflow is collimated in a narrow beam. Okay, a typical opening angle for a long duration GRB is about 5 degrees. So that means that we see these gamma ray bursts only when they happen to point directly at us, about 1% of the time. So for every event that we see, there are over 100 that we don't. I'll come back to that a little bit later, so please hold off on that. Okay, so in order to understand gamma ray bursts, in order to study them, that means that it's not enough to just find the gamma ray emission and then move on and find the next event in gamma rays. all the information that we have, for example, the opening angle of the jet, the energy of the explosion, the nature of the environment, doesn't come from the gamma ray emission, it comes from the afterglow. So we really have to follow up on these detections with a wide range of telescopes, and as I showed you, we have to do it all the way from X-rays to radio. So the program I've been running at Harvard for the last 8 years or so essentially utilizes alerts coming in from the SWIFT satellite in real time, and then we use target of opportunity programs at places like Magellan, Gemini, MMT, other large ground-based telescopes, various space-based telescopes, and radio and millimeter wave telescopes to get a complete picture of the afterglow emission, and subsequently also study the environment in which these sources happen. And as I'll show you in this talk, the nature of the environment, the galaxies and the locations of the explosions within the galaxies provide an extremely powerful tool for understanding the progenitor systems. So before we get into short GRBs specifically, let me just show you the lines of evidence that connect long GRBs to the core collapse of massive stars. There are essentially three primary lines of evidence. The first one that people noticed is that long GRBs only happen in star-forming galaxies. So we've never seen a long GRB happening in a galaxy that does not have active star formation. That is an indicator that those kind of events are related to star formation activity, therefore to massive stars. In addition to that, if we look at the distribution of long GRBs within their galaxies, how are they distributed relative to the stellar light in those galaxies? So that's shown here in this red curve. It tracks the distribution of star formation within the galaxies. Okay, so they're spatially distributed within their galaxies just like star formation is, again showing that they are directly related to the star formation activity. And then the most direct link is the fact that we see in the nearest gamma ray burst where we have enough sensitivity, we see actual signatures of a supernova explosion that happened at the same time as the gamma ray burst. In particular, supernovae of type 1c. So those are massive stars that have lost their hydrogen and helium envelope before they exploded. So very compact, massive stars. Okay. So we have both kind of a smoking gun signature. We see an explosion of a star at the same time as a gamma ray burst. And we also see from the environment that they are related to star formation. Okay, so keep those things in mind because I'll show you how short GRBs are very different from this picture. So the leading model that's been around for explaining short GRBs, in fact, this model predates the understanding that there are two types of GRBs. So this was really the leading model for explaining all GRBs for many years, is the mergers of two neutron stars in a binary system or a neutron star in a black hole. So the idea here is that this merger leads to the formation of a black hole that then accretes debris from the outer envelope of these two neutron stars, and it can power a gamma ray burst. Now this model has some very clear predictions that have been laid out many years ago, but we've, until recently, never had the data to actually test these predictions, but now we do. So let me walk you through some of these predictions, and then I'll show you kind of one at a time how the observations actually satisfy these predictions. So first of all, we don't expect in this case, unlike in the long GRBs, we don't expect an associated supernova at the same time as the merger. There is no supernova here that's happening. They're not massive stars. We expect these systems to happen in a diverse set of environments. And the reason is that the time scale between the formation of the two neutron stars and the eventual merger can be short. It can be tens of millions of years, so recently after star formation. And it can also be very long. It can take billions of years, in which case these events would no longer be associated with any star formation activity. So we expect diverse environments because of this broad distribution of delay times between the formation and the merger. In addition, we expect that these systems, when they form, when each one of these neutron stars forms, it forms in a supernova explosion and it receives a kick. And we see this in pulsars. There are some pulsars that travel at velocities of up to 1,000 kilometers per second due to asymmetries in the supernova explosion. So we expect these binaries to also be born with some sort of a kick that will cause them to drift away from where they were formed. And if it takes hundreds of millions of years to merge and they're traveling at 100 kilometers per second, they will merge in a very different environment from where they formed. So that will imprint in large, potentially large offsets from the galaxies in low density environments. Another expectation of this model, or at least something that is an open question, is whether these systems are the dominant source of this process nucleosynthesis process. The reason is that when two neutron stars merge and material is ejected from these neutron stars, it's by definition neutron-rich material. And so it is an attractive site for this R process. And of course, the most direct signature of this process is associated gravitational wave radiation. I mean, this is exactly the system, the type of system that LIGO was built to detect. All right, so let's go through these and look at them one at a time. So the first one is relatively straightforward. So we have observations of short gamma ray bursts relatively nearby, and we can go and search for a supernova association for these events. So here's an example of a fading afterglow, and this is what a supernova should look like if it was there, and these are the observational upper limits. Okay, so clearly we rule out that there was a supernova associated with this particular short GRB. Now we can look at additional events. So here is the distribution up here at the top of the supernovae associated with the long GRBs. You can see that they're tightly clustered. They're not standard candles like type 1As, but they're fairly uniform in their properties. And these are upper limits from short GRB observations. What's interesting is that all of these short GRBs were specifically chosen to be in star-forming galaxies. So these galaxies have active star formation. There are massive stars born and exploding in these galaxies, but these short GRBs do not have associated supernovae. So they are not related to the star formation activity in a direct way. Yeah.
What is the origin of the 10 to 20 day delay?
Yeah, so in supernovae, the optical emission is dominated by the radioactive input from nickel-56, which is synthesized in the explosion, and the half-life is of order a week or so. So that's the characteristic constant. Yeah. Okay, now the other expectation was that they will happen in diverse environments. So here are 3 examples of short GRBs that are associated with elliptical galaxies. Okay, so here's one case. Here we have a more precise position. You see the afterglow over here. It fades away right outside of this elliptical galaxy. Here's another one at redshift of 0.9. And in all of these cases, the stellar populations are very old, at least a gigayear or several gigayears old. So clearly, these galaxies have no massive stars left in them, and they produce short GRBs. So short GRBs are not related to massive stars. Okay? It doesn't tell us that they're neutron star binaries, but at least it's a clue that there's something else compared to the long GRBs. We can gain a bit more detailed understanding by looking at the breakdown of the galaxies. How many of them are star-forming galaxies, and how many of them are early type elliptical galaxies? We find that there is an overabundance of short GRBs in star-forming galaxies, very similar to type 1A supernovae. And that means that both star formation and stellar mass play a role in regulating the rate of events. What that means is that a galaxy of a given mass that had recent star formation activity will have more progenitors of short GRBs than a galaxy with the same mass that does not have star formation. And that means that the delay time distribution is broad. There are some that merge very quickly after star formation, and there are some that take a very long time. Consistent with the distribution, where the probability of merger time scale goes like the merger time scale to the -1, which again is very similar to type 1A supernovae, and is also identical to what people infer from neutron star binaries that we know of in the Milky Way. Okay, so we have of order 10 or so system in the Milky Way that have this kind of distribution. So it's again suggestive of a link. Okay, so we had 2 predictions. Both of them are now borne out by observations. There are no supernova associations. There's a broad delay time distribution. Okay, so let's take a look at the next one, this idea that some of them have kicks and have traveled outside of their galaxies. So in order to look at this question, it's no longer good enough to just look at the integrated properties of the galaxies. What we want to understand is, where did the short GRB happen within its galaxy? And for that, we need high angular resolution from the Hubble Space Telescope. So here are some examples of observations we've been doing with Hubble of galaxies that hosted short GRBs. In each case, the circle marks the 5 sigma uncertainty in the position of the GRB. Okay, so you can see that we can locate them very precisely within their galaxies. And already from these images, you can see without any statistical analysis that some of them are happening fairly far outside of their galaxies. Right? So all the stellar light is here, the short GRB is here. But some of them are close to the galaxy. So we want to look at the distribution. Oh, this one. Yeah, sure. I mean, it could be in front as well. So all we know is the projected separation, right? That's all we know. Now, before I show you the full distribution, I'll show you something that puzzled us for a while until we, I think, figured out something really interesting, which is in some of our follow-up observations for about a quarter of these systems, we couldn't find an obvious galaxy. Okay, so clearly these things are associated with galaxies, but we just couldn't figure out what the galaxy was. So here are two examples. The crosshairs mark the position of the GRB, and you can see that there is no obvious galaxy around that position. There are other galaxies nearby, but nothing close to the position of the GRB. Nope. Yes. That's a convention of astronomers because we look up. Yeah, that's how astronomers view the universe. Yeah. Yep. Okay, so we have about a quarter of the cases where we don't see an obvious galaxy, and in principle, you can imagine that those might be the systems that had such a large kick when the system was born, and have been traveling for a long enough period of time that perhaps they came from this galaxy and traveled all the way up to here before the system merged and produced a gamma ray burst. So how do we test this idea? How do we answer that question? Well, we can do it statistically. So what I can do is I can take each one of these galaxies in the image and ask what is the probability of that galaxy being there by pure coincidence. Okay? And that probability is related to the product of the number density of galaxies on the sky of a given brightness. Right? There are more faint galaxies in the sky than bright galaxies, and the area over which I'm searching. So if I find a galaxy over here and this probability is close to unity, then I don't get excited about this. It's there by coincidence. If I find a galaxy and its probability of being there by chance is very low, 1% or less, then I might argue that it is actually related to the GRB. It's not there by chance. It is the galaxy that hosted the progenitor system. Okay, so we did this analysis for all of these fields that where the GRB did not have an obvious galaxy. And what we found is this distribution of probabilities. So there are no galaxies nearby within about an arc second. That's by definition. And then you can see that we find galaxies, but they have fairly high probabilities of chance coincidence. But at a separation of a few to maybe 20 arc seconds in these fields, there are galaxies with very low probabilities of chance coincidence. Okay? So in this particular case, it's this galaxy over here. The probability of that galaxy just being there randomly relative to the position of the GRB is less than 1%. All right, so this argues that these galaxies, that these systems are coming from these galaxies at large offsets. Now, when I showed this to people early on, people said, well, you know, maybe this has nothing to do with GRBs. Maybe it's something about galaxy clustering, this or that or the other thing. So we decided to repeat the analysis for systems that had a galaxy exactly at the position of the GRB. And if it's something to do with galaxy clustering, we'll see the same signal there. Okay, so this is what we find. So in that case, of course, there is a low probability for the galaxies that are exactly at the position of the GRB. That's expected. But you can see that we don't see the same signal. Okay? In those fields, we don't see galaxies at large separations with a low probability of chance coincidence. So this is telling us that there is really a direct physical correlation between the galaxies at these very large separations and the position of the GRB. So we have spectra for these galaxies. We know the redshifts, and so we can measure the projected distance on the sky. And these separations are somewhere in the range of 50 up to 100 kiloparsecs. So that means that these systems, whatever caused this gamma ray burst, had to travel a very large distance from where it was born. And the idea of kicks in neutron star binaries is a natural explanation for this. Now, to convince you that that's the case, we can look at the overall distribution. So this is the cumulative distribution of projected offsets in kiloparsecs for short GRBs in red, and then long GRBs in black, and green and blue are core collapse and type 1a supernovae. And you can see that for the short GRBs, there is quite a large range, all the way from about a kiloparsec for the smallest separations, up to almost 100 kiloparsecs at the largest separations. And what's also drawn on here, these gray curves, are predictions from population synthesis models of neutron star binary mergers, where they take large numbers of neutron star binaries with a distribution of merger timescales, kick velocities, and host galaxy potentials, and they just let them evolve and find out what is the distribution of separations by the time of merger. You can see that it shows the same trend of very broad distribution from small offsets all the way up to tens and even hundreds of kiloparsecs. Okay, very similar to what we see in the data. Okay, so we think that that's a clue for these kicks actually happening in short GRBs. Let me skip this. Okay, so we had this prediction that kicks will lead to large offsets, and we actually see these large offsets in the data. And again, if you notice in the previous plot, we don't see those kind of offsets for other types of transients. We don't see them for long GRBs or for type 1A or core collapse. Okay, so what comes together with these kicks is the local environment of the GRB having a low density. That would be another prediction of that. So how do we measure the density in the local environment? Well, now I'm talking about a scale of about a parsec around the explosion. So we can't measure it directly, but we can measure it from the properties of the afterglow. So here's an example of an afterglow that we observed. So here are radio, optical, infrared, and X-ray observations. And by fitting this data with just basic models for how the afterglow evolves as a function of time, we can infer properties like the kinetic energy, the density, and we can place some limits or measure the opening angle of the jet. So in this case, we find that the density is somewhere between 0.01 and 0.1 particles per cubic centimeter. That's lower than the typical density of the interstellar medium. Here are two more examples where we have these kind of detailed observations. Here the density is 2 times 10 to the minus 3. Here the density is again 0.01 to 0.1. So 3 cases where the densities are much lower than the typical densities of the interstellar medium. Now, to get these measurements, we need data spanning all the way from radio to X-rays, which is very difficult for short GRBs. In fact, you're looking at the complete sample of events from which we have this kind of data. So if we want to address this more systematically, we need to do it again in a bit of a statistical sense. Okay, so we can do it by looking just at the luminosity of the optical afterglow. So the luminosity of the optical afterglow depends on 2 parameters: the density to the power 1/2 and the kinetic energy to the 4/3 power. So what I'm showing here is the optical luminosity of GRB afterglows at some fixed time in the rest frame, 6 hours, chosen somewhat randomly, versus the isotropic energy inferred from gamma ray observations. So that stands as a proxy for the kinetic energy. Okay. Now in red, I'm showing the long duration GRBs, and in blue, I'm showing the short duration GRBs. So in both cases, you see a correlation between the optical luminosity and the gamma ray energy, and that's because the optical luminosity depends on the energy to the 4/3 power. So that's exactly this correlation. But the other thing you see is that there is a difference between the correlation for the long GRBs and the short GRBs. There is a systematic offset in that correlation. And that systematic offset comes from the density being systematically lower in the environments of short GRBs compared to the environments of long GRBs. Okay. And that offset requires a density that's about 30 times lower on average. Okay. So it's not telling us exactly what the density is, but it's telling us that it is systematically lower than the environments where star formation is happening. Again, being a clue that these things are happening in low density environments. Okay, so now to the jets, and I'll answer the question of how we measure the opening angles. So it's a bit of a digression talking about density, but we measure the opening angle of the jet also from the afterglow. So the signature we look for, so the afterglow emission just declines as a function of time. The signature that we look for to infer the presence of a jet and to measure the angle is a break in the decline rate and a steepening. And the reason this happens is that at early time, we see only a small fraction of the jet angle because the Lorentz factor is high enough that relativistic beaming limits the area that we see to be smaller than the size of the jet. As the Lorentz factor declines with time, at some point it will get to the point where 1 over the Lorentz factor is exactly the opening angle of the jet. And from that point onward, we essentially see that there is an edge and there is no more radiation coming out from outside of that angle. And the radiation will steepen. Okay? So by reading off the time when this happens, we can infer the angle. The earlier this is, the narrower the angle. So here we have a distribution of opening angles for long GRBs in red. You see that we have quite a few measurements, and they're typically somewhere in the regime of 5, 7, maybe 10 degrees. And then here are the observations for short GRBs. There are only a few measurements and some upper limits. But it seems like the typical opening angles are very similar. They're also in the range of 5 to 10 degrees. Okay, so I'll take 10 degrees as kind of a fiducial number here. So that measurement allows us to correct the energy scale. We have to correct from a spherical explosion to a collimated explosion, and it also allows us to correct for the event rate. So for the energy scale, it means that the typical energy of a gamma ray burst is only 10 to the 49 or a few times 10 to the 49 ergs. Okay, that's actually much lower than the energy of a supernova explosion and lower than the energy of a long duration TRB. What's interesting is the rate. So the observed rate of short duration gamma ray burst is about 10 events per gigaparsec cube per year. But now we have to correct it for this beaming factor, and I can recast that rate by asking how many events would I expect at all orientations within the volume that advanced LIGO will be sensitive to at design sensitivity, which is about 200 megaparsecs. And that answer is about 10 events per year. Okay? So our prediction from associating short GRBs with neutron star binary mergers and then making the beaming correction is that once the advanced LIGO gets to design sensitivity, it will detect about 1 neutron star binary merger per month, okay? Which will be fantastic, easily testable too. So if they run for a year at design sensitivity and they don't see any neutron star binaries, then you can send me an email saying I was wrong. Now there's a slop of a factor of few here, so maybe it's as low as 3 events per year, maybe it's as high as 30. Okay, so low density also passes the test. Okay, what about this R process nucleosynthesis? So what's the deal here? Okay, so the idea here is that there is going to be, in this merger, even though we form a black hole with an accretion disk, some of the material is dynamically ejected from the system at the time of the merger, and some of it can be driven off of the accretion disk through winds, and that material is neutron rich. And as it expands and decompresses, it will undergo nucleosynthesis, and in particular, the R process, building up to very heavy elements, so atomic numbers of 100 and beyond. Now, this material, especially material produced by the R process, is radioactively unstable. There are a lot of different isotopes with different half-lives, spanning all the way from milliseconds to days and weeks. And so this, very much like in a supernova, the radioactive decay of this material will be a source of heat that will manifest as optical radiation. Now, the difference from a supernova is that the velocities of this ejected material are higher. They're about 10, maybe up to 30% the speed of light. In a supernova, it's more like 10,000 kilometers per second. But there's a lot less of it. Okay, so in a supernova, the amount of material that's in the explosion is anywhere from 1 to a few solar masses, and maybe 1% of that is radioactive material. Here, almost all of it is radioactive, but at most there is about 1/10 of a solar mass. So what this means observationally is that the luminosity of the transient that's produced by this radioactive decay is going to be significantly lower than in a supernova, because there's less radioactive material. And also because it expands rapidly and there is less of it to absorb light, it will become optically thin much faster, and instead of a characteristic timescale of about a week for a supernova, the timescale will be days. Okay, so it's going to be a fast and dim transient associated with this. Now, the other interesting result that came out in the last couple of years is that early on it was assumed that those would be the primary differences, but the spectral energy distribution would look very much like a supernova, where the dominant source of opacity is the iron peak elements. Okay, so that leads to this cutoff below about 4,000 angstroms. Now, it turns out that people have started looking into these R process products in more detail, using data from places like Los Alamos. Some of it used to be classified and it's not classified anymore. And they realized that some of the elements that are produced in this process, in particular the lanthanides, have extremely high opacities, to the point where they cut off the radiation very strongly below 1 micron. Okay, so what this means is that the spectral energy distribution is shifted from the visible band into the infrared band. And so the luminosity is lower in the optical, but the time scale is stretched out. So the overall energy output is similar. We're just going to get something that is dimmer even than expected before, but will last a little bit longer, but most of the radiation coming out in the infrared. All right, so these papers pointing this out came out in 2013, and then in June of 2013, we had an opportunity to actually go and test this idea. So what I'm showing here at the top are observations of a short GRB taken at Magellan. So this image was taken a few hours after the burst. You can see a bright source here that was gone a month later. So this is the difference between these two images. So this is the galaxy, it's still there, and then the afterglow faded away. And then we did observations with Hubble in the visible band in F606 and in the infrared band. So the first observations here were done about 10 days after the event and a month later. And when you difference these images, you can see that in the optical there is no residual emission. So in the optical, by 1 week after the event, all the emission was gone and was not detected again. But in the infrared, there was, even 1 week after the event, there was still bright emission, significantly brighter than in the optical. Okay, so if we look at the brightness as a function of time, what we see here is the afterglow at early time just fading away. Okay, in blue is the optical, and in red is the infrared. And then on this time scale of about a week or so, we see this excess emission in the infrared without accompanying optical emission. So this is exactly the signature that we look for this radioactive, radioactively powered component. And the curves here are a range of models for this emission in the infrared and in the optical. Okay, so you can see that our measurement falls kind of in the mid-range between the expected range of brightnesses. Okay, so this is our strongest evidence so far for this our process nucleosynthesis actually happening in a neutron star binary merger, or in a short GRB that is presumably a neutron star binary merger. Okay, so this is the sum total of it. It's one data point for one GRB. So of course, this is something that we want to do again, and many of you know the Hubble proposal deadline is tomorrow, so we're going to put in a proposal to try to do this for a future event. The tough part is that we need an event that's relatively nearby, within a redshift of about 0.3, and the rate of short GRBs within that redshift range is about 1 every year or two. So the sample is not going to grow dramatically. Okay, so I'll put a question, a check mark here, but it's a check mark with a question mark next to it. All right, so that leads me to the final point, which is gravitational waves. Okay, so we expect gravitational wave radiation to precede the actual merger, and one expectation would be, if this picture is correct, is that we should be able to see simultaneous detections of gravitational waves coming in from LIGO and a short gamma ray burst being detected by a gamma ray satellite. But it's not just a gamma ray emission. As I told you, there is this afterglow emission, and then there is this isotropic radioactively powered component. And so we want to use all of the information that we've gathered from observations of short GRBs to ask the question of what would the electromagnetic counterparts of these sources look like, both when we view them on axis and when we view them away from the axis of the jet, which is going to be the majority of the time. Okay, so first you should ask, why do we want to why do we need to find electromagnetic counterparts to gravitational wave sources? Isn't the gravitational wave data enough? It's amazing, right? And there are several reasons that we actually want to do this. The most basic one is that gravitational wave detectors are good at detecting sources, but they're really poor at localizing them. And if we want to understand basic things like what is the distance to the event, we need to find a precise position that will then allow us to associate the object with a galaxy and measure the distance of that galaxy. If we want to understand how these binary systems actually formed, we want to put them in a broad astrophysical context. We want to ask what kind of stellar populations are they associated with? What kind of galaxies do they come from? We can't do that if the position on the sky is 100 square degrees. We need to narrow it down to an individual galaxy. And the only way to do that is with electromagnetic radiation. The other thing that gravitational wave data does not tell us is what happens after the merger. Right? So we have this merger. It produces all the gravitational wave emission. Once the merger is over, the gravitational wave signal dies. But what happens at that point? Do we always form a relativistic jet? Do we always have our process nucleosynthesis? Do we always form a black hole? Right? So those are questions that we can address through the electromagnetic signatures, not through the gravitational wave data. So there are several reasons, very important reasons, that we want to undertake this kind of analysis. There's also a wide range of possible counterparts, some of which I've already told you about, a gamma ray burst, a short duration gamma ray burst. This isotropic, radioactively driven optical or infrared component. And also, this same component, this material that's flowing out, will interact with the surrounding medium and produce radio emission. Okay, so they are both beamed anisotropic, relativistic, and non-relativistic counterparts that we expect that produce their radiation all the way from gamma rays down to radio waves. Okay, so lots of opportunities to find electromagnetic counterparts. The question is, how bright are these counterparts and how are they matched to our observational capabilities at these different frequencies, especially when we have to look at large areas in the sky of 100 square degrees or even larger. Okay, and so that's a study that we undertook along with Brian Metzger back in 2012. We wanted to do a real systematic survey of what are all the possible counterparts, what are all the observational capabilities that we have, how are they matched? So let's look at the easy one first. We want to see a gravitational wave detection and a short gamma ray burst at the same time. Okay? We can predict how often that's going to happen by looking at the redshift distribution of short GRBs. So already you can see that the nearest short GRB we've ever found is about redshift 0.1. That's already outside of the detection capability of advanced LIGO. Okay, so in 10 years of observing short GRBs, we've never actually seen one close enough that LIGO would have detected it. Part of the reason for that is that Swift only sees about 15–20% of the sky at any given time. So if we have a gamma ray satellite that can see a larger area of the sky, we can take that redshift distribution and extrapolate it to an all-sky rate. And then we can ask, okay, to the distance that advanced LIGO can detect a neutron-star binary merger, how many times per year would we get a coincident gamma ray burst and a gravitational wave source? And the answer is 0.3, so 1 every 3–4 years. All right, so that's what we have to work with. Once every 3 to 4 years, we will have a coincident gravitational wave detection and a gamma ray burst. Those events are going to be the golden events. The jet will be pointed right at us. All the emission will be bright, all the way from gamma rays to X-rays to visible light and radio. But it will only happen once every 3 or 4 years. So what do we do the rest of the time? We want counterparts for a large number. So the other possibility is the optical afterglow. So the optical afterglow is also bright, but unlike the gamma ray burst, we can see the optical afterglow even if our initial orientation from the jet was off axis. And the reason is that the jet spreads as a function of time, and eventually, even if we're oriented off axis, it will come into our line of sight and we could see the optical emission. Okay, so here we have measurements of optical afterglows, and we can see that so this is on axis. On axis, you can see that at 200 megaparsecs, they're bright. They're about 17th, 18th magnitude. Okay? You can detect these with a 1-meter telescope easily, if you have a wide field of view that can look at a few hundred square degrees. But again, the on-axis case is going to happen once every 3 years. So how do these things look like when we view them off-axis? Well, we have all the data, so we can just simulate what they would look like off-axis. So focusing on the yellow and green curves here, which bracket the observations, if we now go off-axis by twice the opening angle of the jet, away from the axis, the green and yellow curves look like this. So by going off-axis, what this causes is a delay in the time at which you see the emission. That's the time it takes the jet to spread enough to come into the line of sight. And at that point, you can see that it's already much fainter. So for the yellow and green curves which bracketed the data, there will be a delay of somewhere between 1 and 10 days. And the brightness will now be 23rd to 25th magnitude. Okay, so now that it's no longer the realm of 1-meter telescopes, that's the realm of LSST, Pan-STARRS, dark energy camera. And that's when we go only twice the opening angle away. If we go any further than that, we drop very quickly to 38th magnitude, and then nobody can read this. Okay, so the fraction of events that will be contained within this somewhat wider angle is only about 10%. So we're doing better than the gamma ray emission itself, but it's still only 10% of the events, and we need to use big telescopes to do this. Okay, so what about the radioactive component? Right, so the relativistic jet component is tough because you have to be along the line of sight or very close to it to see anything. But the radioactive component is isotropic. So that's good. That can be seen in principle for every event. You can see it from every angle. But remember what I told you, the emission is primarily coming out in the infrared. And in the infrared, we don't have wide field telescopes, at least nothing that is sensitive enough. So that means that we have to do this in the optical, kind of on the tail of the spectral energy distribution as it's dying off. So we looked at this question by essentially running simulations of various models, putting them at different distances and asking at different bands between, let's say, R, I, and Z band, so about 0.6 microns, 0.7, and about 0.9 microns, how deep would you need to go to detect a certain fraction of these counterparts? So let's look, for example, at the 50% line. Okay, so that's the cyan line. So it's saying that at R band, the typical brightness to get 50% detection rate is about 25th magnitude. Okay. So that's very difficult. The only facility that's coming online that can do this over a wide field of view is LSST. And that's at 50%. But it gets better as we move to the red because we're climbing up on this absorption tail. So in I band, it's 23rd magnitude, and in Z band, it's 22nd magnitude. Okay, but these kind of magnitudes, in order to detect this kind of emission, again, we're talking about deep observations with wide field instruments on 4 and 8 meter class telescopes. Okay, so they're, I can count on one hand how many telescopes like that there are around the world. There are really only a handful, but that is really what's required in order to make these kind of detections. And the other question that comes up with this kind of search is, okay, so we want to find some really faint optical transient in 100 square degrees. Aren't there going to be a lot of other faint transients in 100 square degrees that will confuse our ability to identify it? And the answer is yes. There are going to be hundreds of transients in that search area when we go to these kind of magnitude levels. Luckily, here, the unusual spectral energy distribution that makes it so difficult to detect these sources to begin with helps us in identifying them compared to other transients. And the reason is that because of these unusual opacities that are only coming up in the context of these events, they're significantly redder in color than any other transient that we're aware of. So we've done here a comparison to various types of transients, some of which are known and have been seen in large numbers, like type 1a supernovae. Some of them we have small samples, some of them are theoretical models. But in all cases, we find that this radioactively powered transient is significantly redder in color. And that is the main way to discriminate between that event and the many tens or hundreds of contaminating sources. Yes. So, I'll come back to this. That's essentially our strategy. So color information is key to making this identification. So we looked at that question of dust. So for example, if you want to take a type 1a supernova and make it as red as this, the amount of dust you need to add is so large that it will dim these supernovae below detectability. Okay, so you will only see the really, really nearby events. And then the numbers are manageable. Well, this is the I minus Z color. Yeah. Okay. All right. So that's the theory. Now, have we actually done this in practice? Well, we did. As many of you know, LIGO in its first observing run about a year and a half ago detected 2 gravitational wave sources. One on September 14th of 2015, one on December 26th. Here are their localization regions on the sky. Okay, so you can see how terrible it is. So this one was 600 square degrees, and this one was 1,000 square degrees. Right, so that's the challenge. Of course, it's almost impossible with any given facility to follow up this entire region, especially when they're large enough that they span both the northern and southern hemispheres. So you have to use at least 2 telescopes. The other challenge is that these were black hole binaries, not neutron star binaries. Okay? In particular, the first one was a 36 plus 29 solar mass black hole binary merger. The second one was 14 plus 8. These events are not expected to have any electromagnetic counterparts. There's no obvious reason that they should. We can always cook up some theory, but they're not expected to have these counterparts. But we've been given time on the dark energy camera to do these rapid follow-up observations. And the idea was twofold. First, they didn't tell us that they were black hole binaries when they sent the announcement. They forgot to mention. So that information only came in about a month after we finished the observation. So I wish they told us. But at the same time, we wanted to actually see if we can carry out this set of observations, if we can image these large areas on the sky, if we can do real-time identification of contaminating sources, of a potential counterpart, really test the whole system. Okay, so here are our dark energy camera observations of the first event. So we could get the part of this arc that was in the southern hemisphere. There are two sets of localizations here. There's the solid one, which is the one that was the final localization announced in the publication of the event months after it was discovered. And you can see that this is the ridge of highest localization, and we pointed our telescope here. So why did we do that? Well, it's because initially they told us that this was the highest region probability. And then they shifted the whole thing by something like 20 degrees off. And it's a black hole merger, yeah. But we carried out these observations. We covered about 25% of the localization area. We achieved our depth of observations. We found a lot of sources that we managed to reject using our I-Z color criteria. Again, we didn't know what we were following up. But we had one event that looked very interesting and very promising. Okay, so you can see our set of observations here, December 28th. The event was December 26th. Okay, so there was a 2-day delay between when they found it and when they announced it. So December 28th, January 1st, January 8th, January 18th. We have a transient over here on the edge of a galaxy. Kind of looks like the short GRBs that I showed you in the previous images. It fades very rapidly. It's gone in a few days. That's much faster than a timescale for a supernova. And its I-Z color was about half a magnitude. So not quite as red as we expect, but again, redder than most transients. Okay, so we got really excited about this. You know, we found something that really looks like the counterpart. Okay, so here are the observations here. You can see it dropping off very rapidly. Then we went into the all the existing archives to see if there was a redshift for this galaxy, what we can find out. And what we found is that this event was discovered about 3 months before the gravitational wave event, independently by the Pan-STARRS project. So what we found is that this is a type 2P supernova. It was on the plateau for about 100 days, and we happened to catch it exactly when it was falling off the plateau. And when a type 2P supernova falls off that plateau, it decays very rapidly and it becomes very red. Okay, so a really unusual set of circumstances, and something that we never anticipated as a potential contamination source for these kind of searches. But here it is. So it does happen that even a transient that has a very long duration, more than 3 or 4 months, can appear to be rapidly fading and very red if you just catch it at the wrong time. Okay, so we already fit models to this, and we're very excited. So so that means that these kind of searches are not going to be trivial. We're going to find events that masquerade as counterparts for these sources, and part of the our follow-up effort is to identify these things in real time, get spectra to see what they are with Gemini South, and then we have a program at Chandra to do X-ray follow-up and a program at the VLA to do radio follow-up. So get a complete picture of these events. Okay, so the system works. What's going on in the second science run, which is going on right now, I can't tell you. If I tell you, I'm going to go to LIGO prison or something like that. So LIGO is up and running. They started their second science run in December of last year, and it will go through the end of August of this year. The sensitivity of the detectors is comparable to what it was in the first science run. So you can kind of extrapolate and guess what it is that they're probably finding that I can't tell you about. But that's where we are now. So we haven't, our program with the dark energy camera is active. We've been given sufficient amount of time to follow up to 2 events and actually do target of opportunity override of any program that's on the telescope, not just the dark energy survey, but any program on the telescope. And we've exercised that system without actually triggering. We did kind of a simulated event to see if the observatory can respond, if we know what to do. And we scared the hell out of a couple of observers who were at the telescope who thought that they were going to lose their entire observing time. But that's the plan, you know, to kick people off the telescope. It's really the only way to do this. Okay. And the plan will be to continue this follow-up as LIGO improves its sensitivity in the third science run, and then eventually when they get into routine science operations in 2019 and beyond. Okay, so let me just summarize. So we've carried out a wide range of observations of short GRBs, both of the events themselves and of the galaxies that they happen in. We found that they have a broad distribution of delay times, diverse set of environments. There's evidence for these kicks, large offsets from their galaxies, and potentially evidence for our process nucleosynthesis. All of these lines of reasoning connect short GRBs to neutron star binary mergers. The real smoking gun will be seeing gravitational waves in a short GRB at the same time. We have evidence for beaming, telling us that the event, I see a typo here, this used to be 10 events per year, now it's gone up to 20. The event for that LIGO will event rate for LIGO for neutron star binary mergers that we predict from the short GRB observations is about 10 events per year. Now, just to remind you, to some extent, we've seen already the on-axis electromagnetic counterparts of neutron star binary mergers, short GRBs. But we know that the vast majority of sources that LIGO finds will not have an on-axis jet. So using this information that we've gathered for short GRBs, I think we're in a position to understand how to do the electromagnetic follow-up and what the expected counterparts are. And the next step is to actually get a neutron star binary detection from LIGO and find an electromagnetic counterpart. And when that happens, I'll be happy to come back and tell you all about it. Okay, I'll stop there. Yeah, so people in fact have made such claims in the past that you can standardize the energy scale of GRBs to the point that if you can measure the gamma ray properties, you can measure the opening angle of the jet, you can use them as a distance indicator. These claims have been met with a lot of skepticism for a couple of reasons. One is that it's fairly messy physics and it's hard to imagine that that would actually work to begin with. And the other one is that it's a bit of a circular argument because, for example, with type 1a supernovae, the way this works is that you have a local sample of events whose properties you know very well that you use as an anchor for your distance scale. And then you go and find them at higher redshift and you measure the cosmology from that. We don't have nearby gamma ray bursts. All of them are at large distances. And so in order for all of this to work, you have to begin by assuming the cosmology. And then run it kind of in a circular way by saying, well, I assume the cosmology and then they seem to be standard candles, and so I can use them for cosmology. But there's no kind of independent check. No, it's just that the event rate is very low. These are really rare events. So the rate of GRBs per unit volume of the universe is about 1,000 times lower than the supernova rate. So there's just not enough volume in the nearby universe that will find these events at any reasonable rate. Yeah. So the idea is that these kicks are given to the individual neutron stars when they're born, but that gives imparts momentum to the whole system. So the system is traveling out at some velocity, tens, maybe even hundreds of kilometers per second, as it's spiraling in over hundreds of millions of years. So by the time it merges, it has traveled a substantial distance. Oh no, it doesn't necessarily have to be in the same direction. It's just a combination of the two. Right? Yeah, as long as you don't disrupt. Yeah. So in some cases you will disrupt the system. Right? So if the kick is too large, you can unbind the system, then it's game over. You have two separate neutron stars. Yeah, yeah.
Gravitational waves,
Mhm.
are they isotropic?
Mostly isotropic, but there is some angular dependence of the strength of the radiation. So, for example, it's easier to detect systems that are face-on relative to the detectors, okay? Along the angular momentum axis, which is also the expected axis of the jet. So, in principle, a system that has, you can see those systems a little bit further away than the average neutron star binary merger. And we actually build it into these rates of, when I said it's one event every 3 years, the distance I was taking there is not the canonical 200 megaparsec for the average neutron star binary. It's more like 300 megaparsecs because you get this boost for the face-on system. No. Oh yeah, so I didn't use that terminology. It's a bit jargonish, but the idea is that if you look at the luminosity of this radioactively powered transient, it's about 1,000 times brighter than a nova, so a kilonova. The name stuck, not my name. But, yeah, so people have been doing this. It's easier to do it for the long GRBs because the energy scale is much larger, and so you can see them much further out. There are a couple of claims of optical transients detected without a gamma ray burst that seem to look like an off-axis afterglow, but they're not definitive enough. The timescales are still relatively short, so you need a cadence, a survey with a cadence that's fairly rapid compared to most of the surveys that are being done right now. And most of the ones, like DES, for example, is looking at an area on the sky that's just too small to have a chance of capturing this.
So the other, when you get the R process, is a normal profile supernova. Are you suggesting to replace the R process?
Yeah. So first of all, that's not my original suggestion. I mean, I think that debate has been in the literature much longer than I've been around. But I would say that there are two kind of arguments going, or more than two, that are starting to point in the direction of neutron star binary mergers. One is, this observation that I showed. The other one is that the most recent simulations that people do of Corpus supernovae, they just cannot get the second and third peak of the R process to come out of the simulation. They're not neutron rich enough. The conditions are not right.
But
Yeah.
you explain the very manifold stars with extremely high R process
Yeah.
that are among the global stars of the galaxy.
Yeah.
Wouldn't get the R process.
So actually, so that was going to be my third line of reasoning, and in fact, I think some of the recent observations that have been done. Jennifer, remind me, what's the system? Is it in Reticulum 2? Yeah. So those are two systems where it looks like the R process abundance in these metal-poor stars is already established, and it's suggestive of enrichment not by a process that has a high event rate and a low yield, which is what you would expect in a supernova, but a low event rate with a high yield, which is what you would expect with a neutron star binary merger. So that's coming from a completely different line of reasoning, I think actually supporting the neutron star binary merger picture. So I think the ultimate thing will be the if we see these in connection with the gravitational wave sources, then it becomes the ultimate thing. Yeah, somewhat limited. So Fermi, the Fermi gamma ray burst monitor sees about 60% of the sky, so much bigger area, and it finds a lot more GRBs than Swift does, but it localizes them to positions that are almost just as bad as the LIGO positions. So almost nobody bothers following those up, which is unfortunate. The large area telescope can provide much better positions, but it has a small field of view, so it detects a few events per year. So it's again not particularly competitive with Swift.